That's also not mine, but it's fine. Hello everyone. Today I'm going to talk about stars and interactions between stars, specifically two kinds of interactions, which I will define shortly in the upcoming slides. So I typically work on stellar dynamics and how interactions shape the evolutions of stars. And I almost always start with this slide. Some of you might have seen, most of you might have not. But this is just a general overview of how stars would interact in their lives. If you look at companions of stars, stars can be isolated, like the sun, and most of their evolution is through single star evolution of nuclear fusion and fragile phases and so on. Then you could have binary stars, which have more stuff happening, like mass transfer interactions, which change their evolution. You can have multiple stars as well, where orbital dynamics adds an extra layer of complexity to this evolution, and these kind of stars can have collisions as well due to changes in eccentricities of the orbit, which brings the stars much closer together to each other. Now we can look at the environment of stars as well, and again, like the sun, you can have isolated field stars which have pretty much no neighbors, and they're not going to interact with any other companions or passing by stars in their lives. Or you could have in between, or stars which grew up in clusters or living in clusters, where perturbations from other stars in their environment can affect how they live. And depending on where each star reside and how many companions they have, you can have many astrophysical phenomena. Binary stars are required for this is the one that are required for kilonovae, gravitational waves, and many more events which we are excited about in these recent years. Multiple stars also can contribute to these, but then with their extra layer of complexity, they can add more interesting physics. With dense clusters, you have other encounters like tidal disruption events, and again, stellar collisions and binary interactions also happening because of binaries in clusters. Or you could have everything as well. So in this talk, I'm going to talk about star clusters, specifically interactions in star clusters. So in dense star clusters, the stellar density can be high enough that single encounters are possible. Binary single encounters are when binary stars and single stars come together. Single are when two stars come together. Typically, binary single encounters are more common, given enough binaries in a cluster because of their larger cross section. But in this talk, we'll stick to single encounters. So these have a lot of implications as well. These kind of encounters are also called resonant encounters, and they can affect the long-term dynamics of stellar clusters. They also contribute to binaries formation and destruction if one of them is a binary, and tidal disruption events and stellar collisions, which is the main focus of this talk. So in this, I'm going to differentiate between these two terms, which people typically might associate as the same thing, and I illustrate them in cartoons here. So when I say collision, I mean two stars encounter each other, like in the previous slide, and if they come close enough to each other, it might not be head-on collisions, but close enough that they would go with multiple passages and eventually become one product. A merger is when you have a binary and due to some processes like tidal dissipation or mass transfer or a combination of everything, eventually merge and become a single thing. So for the rest of this talk, I'll be using these terms. Why are studying such clusters, such encounters important, or such interactions important? Number one is blue straggler formation. Everyone must be familiar with blue straggler stars, which are hotter and brighter than the turn-off of main sequence track in the color magnitude diagram of a cluster. as so. So if you have a color magnitude diagram as in this plot, and this is the main sequence track, you have some stars located there, which are thought to be products of collisions, mass transfers, or binaries, which is why they appear younger and more massive than they ought to be. Another implication of this is magnetic stars or stars with higher magnetic fields than usual. Typically, any magnetic field can be amplified when there is significant mixing of material and there is specifically turbulent mixing of material. This causes stretching, folding, and twisting of field lines, which increases the density of field lines and hence the magnetic field strength. Here, there's a caveat that we are in our simulations, and we are assuming ideal magnetohydrodynamics, which means that magnetic field lines are frozen in to their materials. So whenever something twists, even the magnetic field line twists with the material. Additional complications are expected when there is dissipation involved, but in stellar plasmas, it's expected that this dissipation is not very large compared to the strength of the magnetic field.
So I've always heard what you just said about these magnetic stars, but is this basically, can I understand it as some kind of dynamo mechanism? Or
sure.
Is it something else?
Yeah, sure. So for long-lasting magnetic fields, you would expect some kind of consistent dynamo, which happens in the star. So yes, as we can differentiate between like a small-scale dynamo, which happens in the scale of turbulence, which is happening, and it just propagates to other wave numbers, or you could have large-scale mixing, which could cause twisting in the large scale. But the longevity of that is, I'm not very sure about that, because if there is differential rotation, for example, shearing can cause twisting of field lines or folding of field lines, but eventually there wouldn't be differential rotation, so this would stop. There would be some magnetic reconnection, so the field strength would not be as high. So yeah, this is just an illustration. A field like this could eventually become very twisted, and when there's a high density of field lines, there can also be reconnection and everything. So the density, the magnetic field strength in the long term is a much more difficult problem to deal with than in the short term. So yeah, in this talk, I'm going to talk about, I'm going to discuss MHD simulations, magnetohydrodynamic simulations, using the moving mesh code REPO. And the main motivation of our talk is to differentiate between these collision and merger products, because this has not been something which people have really focused on. It's important to distinguish them, to see what the origins of blue straggler stars are and how they differ from each other.
So you're adding the magnetic field. Is the pure hydro problem well solved for collisions and mergers?
Yeah, there have been, for collisions, there have been many.
But how do they deal with radiative transfer
or radiative transfer?
Or this kind of
yeah,
things?
Usually it's only hydro. There have not been many radiative transfer codes.
No, but does it matter?
Not for the, no, not really. You can just do the hydrodynamic simulation and then put it in a stellar evolution code and how it evolves. Typically, we don't expect radiation to affect dynamics as much unless the radiation pressure is a lot.
Okay,
Unless you have disc
Yeah.
around the.
Okay. Sure, yes.
What if you have a lot of debris from now and things like that? It's very complicated.
Yeah, okay. Yeah, in that sense, yeah, sure. But the disks are not very long-lived, is what people have seen.
Sure.
Especially in
But
collision.
the entropy can change a lot, because I guess going to have
Okay. Yeah. Yeah. So this is the code we use, a repo. I wanted to introduce this code to you. Typically, people solve hydrodynamics problems with two methods. One is the finite volume static grid method, or condition, or whatever coordinates people use, where you have cells divided in a domain and fluid elements associated with each cell, and then fluxes are calculated between cell interfaces, and the fluid equations are solved. Then you have the smooth particle hydrodynamics, where it's a more Lagrangian approach, where the fluid is moving with the particles. So each particle has like a region around it, and they interact with this kernel or region of influence around the particles. A repo is a mixture of both, in the sense that it is a Lagrangian code. Cells move with the fluid, but they are cells. They each have cell interfaces, and fluxes are calculated between them, and everything moves along with the fluid. So it has some advantages of both the methods. Yeah. So in this work, we mainly concentrated on more massive stars, around 5 to 10 solar mass stars. Might not typically expect them to be called blue stragglers, because blue stragglers are usually lower mass stars in globular clusters. But such stars are expected in young star forming regions, and these are also where a lot of more magnetic stars are like massive magnetic stars are expected to be seen. So that is what we aim to look at. On the left is the density profile with respect to radius. So we have for each of the stars. And on the right is the temperature profiles. The solid lines are for the 3D hydrodynamics code which we use, and the dashed lines are the initial stellar models which we get from MESA, which is a stellar evolution code. So we port the density and temperature and all other profiles from MESA into a repo, and there are of course some divergences at very low densities, but that is expected for any code depending on what resolution of star you use.
So just to be clear, that what happened near the surface, the temperatures went up relative to MESA, and that was some relaxation, hydrodynamic relaxation.
Yeah, this is because of relaxation. So yeah, so it kind of tries to measure together with the vacuum internal energy or temperature. I just wanted to take a slide. I wanted to digress a bit and talk about relevant timescales of stars. This matters because in simulations of stars, like these high resolution simulations of star interactions, we can only model in what we call the dynamical timescale, which varies in hours to days, and we cannot model stars using hydrodynamics in longer thermal or nuclear timescales, which go up to kiloyears to megayears. So this is typically the timescale where hydrostatic equilibrium is a role. And this is important because mergers of stars take much longer than these days to happen. So how do we do this? We just use it. They occur due to tidal dissipation, and these timescales are much longer. So our solution is to add an artificial inspiral velocity, which causes them to merge faster. So of course, the advantage is that we can model these interactions better, and more the intermediate phase of mass transfer, which takes place when the inspiral is happening, is not resolvable time-wise in our simulations. However, this does not really matter for the merger product we are looking at, because it's the same amount of mass which is being transferred onto the star. So we want to see the end products, and we don't really care about what happens in the intermediate phases, the exact physics of it. So I show a simulation of collision of stars. Okay, it has to restart. So on the left, we have a slice of density. On the right, we have something called the passive scalar, which is just a way to show how these stars mix. So you initially paint one of the stars blue, one of the stars orange, and then this painted indices advect along with the hydrodynamics equations. And the advantage of that is that you can see exactly what part of the star ends up where. So you know that the core of the new star is the originally less massive star, which was blue in color. So this is just a visual way of to see it. Of course, we can be more quantitative about this as well. And similarly, a merger. You can already see some mass transfer here happening here. This is again accelerated, and we stop the accelerated or artificial in spiral at some point before the actual merger. Already you can see some differences in the exact mixing of the stars. Visual. Yeah.
Well, so you're saying there's a sort of accelerated phase, and then at some point it stops. Is it easy to tell when it stops and turns into that?
Not in the simulation, but the exact physical condition is approximately when they are in contact. Yeah, around this point it stops. And the rest is just, it continues on. Yeah. Okay, so the same collisions I had before, this is one specific case of a collision between a 10 and a 5 solar month star, where the collision impact parameter defined as the ratio of the periapsis distance to the total radius is 0.25. So it's a very close head-on collision. Not completely head-on, but near head-on. So yeah, density profiles, the passive scalars which we saw before, and what we see here is the magnetic field. So our initial stars have we initialize surface magnetic fields at the pole of 1 Gauss, and we assume initially dipole magnetic fields. And as the simulation progresses, you see that there is amplification of the magnetic field due to the twisting of field lines and shear. And the exact initial configuration of the stellar magnetic field is not super important, because there's a lot of mixing happening, and eventually the saturation field would approximately be the same. Of course, the morphology might change, but that is a thing to deal with later. Same with the merger, the density, the passive scalar, and the magnetic field. And here you see here you see something different before. The magnetic field scales were the same as the previous case, as in the collision. But here, I'll just show that again. So the scale is the same. So you can see that the amplification is much more. Okay. There is also a factor of how much angular momentum and energy each orbit contains, because both are not exactly the same. So there is no direct comparison of the magnetic field amplification magnitudes, but we look at other things like the fraction of the directionality changes in the magnetic field, which explains its longevity. Yeah. Here I show the contours of different quantities. On the left is the density, on the center is pressure, and the temperature on the right. This is the face-on view of the collision product. As expected, it's circular, and on the edge-on view, you have the rotational flattening because of the injection of angular momentum, and there's an oblateness to the contours. As you increase the impact parameter, in a sense, if the collisions are more gradual or more less head-on, this structure becomes more and more flattened, more and more disky. In the mergers, however, firstly you see that the contours are way more irregular in the sense that they have not settled onto a dynamically stable state yet. Note that the time here mentioned here is after the merger happens. In the collision case, it was around 100 something hours. Here it is around 200 something hours. So we ran the simulation for twice as long and even more actually, but still this hasn't settled yet. This is because there's a lot of outflows in the mergers happening. It's more clear in the plot of the density where you can see an under density in this region, in the axial regions. And yeah, you also see the rotational flattening here, and that under density is due to actual outflows, which I'll show in the next few slides. Okay. Yeah, angular velocity. So here I show angular velocity of the collision product as a function of the mid-plane radius. So this is the mid-plane angular velocity, and on the y-axis is a fraction of angular velocity to the breakup or Keplerian velocity at that particular radius. I have these different collisions, 10 plus 8 to 7 plus 5 solar mass collisions on the solid lines, and the dashed line represents a collision of a 10 and a 5 solar mass star with a larger impact parameter as compared to the other simulations. You can see that because of the larger angular momentum of that particular initial configuration, its peak angular velocity is also higher. It's closer to breakup velocity. Mergers are also very high up. Their breakup velocities, their angular velocities are also very close to breakup. Excuse me. Yeah.
There seems to be a universal radial law. Do you know exactly
power.
That is? What power that is?
I haven't calculated it, but I will definitely check that.
I'm just curious whether that's Rayleigh instability or something.
What instability?
Rayleigh, like
Okay.
the angular momentum increasing hour or decreasing hour makes a difference between this.
Okay. Sure, I shall check that out. Yeah. Yeah. The takeaway here is that the merger products are rotating faster, but it's also not a major takeaway because the difference in angular momentum is also a part of this plot. And here we show the evolution of magnetic field energies, or which are calculated using the magnetic field strengths with time. Here again, I show the collision plot first on the left. On the y-axis is the magnetic field energy in log scale, and on the x-axis is time. The dashed line shows the time of collision, so everything before that is just the passages. The dashed teal line is for the wider impact parameter, so it takes many more passages to come and collide together to a final product. And because of these multiple passages and multiple encounters, it has more magnetic field amplification as well. We think this is because of injection of, so this is because of turbulent injection at each passage. So this increases magnetic field even more and more at each stage.
So you have a collision with multiple passages. Can you maybe explain the initial conditions a little bit more?
So this is the impact parameter for this particular case, and this is for the other cases. B here refers to the ratio of the argument of periapsis to the total radii of the stars initially. So B is equal to 1 is a grazing collision. B is equal to 0.25 is like much closer to 0.
The impact parameter or pericenter?
Sure. I mean, yeah. So this is a scaled parameter. This is a scaled parameter.
Normally people use impact parameter.
Yeah, impact parameter. Okay, scaled impact parameter, I should say. Yeah. This is just like a notation from, I guess, tidal disruption where they use scaled impact parameters. You see, like an increase in magnetic field at this point. This happens at the first passage of stars, and then it consistently increases. And after collision, there is some mixing. Final mixing here at this point, and then it kind of stabilizes. There's a couple simulations where magnetic field still slightly increases, but then it's expected to stabilize after some time here. The other ones have already saturated.
Sorry, did the stars collide with each other at the first passage and then again at
Yeah, so it goes like this and comes like this.
So they actually did undergo a sort of physical collision.
Yes, so yeah,
and came back.
exactly. So yeah, like in the simulation I showed before.
Pass to each other.
What is that magnetic energy as a fraction of total thermal energy?
Which is the one?
I mean, how big is it?
Oh, as a fraction of total energy, it's around 10 to the minus 6 to minus 4, depending on the simulation. So it doesn't affect the dynamics, if that's what your question is.
So you wouldn't need to treat magnetic fields dynamically. The passive tracers could get the same answer.
Yeah, exactly. So just hide it. Sure, fair enough.
Yeah.
Fair enough. Yeah, magnetic fields are not important dynamically. Yeah, so here's the same thing for the mergers. They are much longer because they take more time. And this is the phase of artificial acceleration. And there's a steep increase in magnetic, there's like a slight saturation here, and there's an increase in magnetic field when Rochelot overflow starts. And then it increases. And finally, again, after merger, it increases quite a bit before saturating. And we see that they're both around 10 orders of magnitude from the initial magnetic fields. So there's a quite significant amplification of magnetic fields. Yeah. And also, in our particular cases here, the mergers have larger magnetic fields. And more importantly, not just larger magnetic fields, their magnetic fields are also, they do not have very small scale reversals. I unfortunately don't have the plot here, but in the collision cases, the magnetic fields have very small scale reversals, which indicates that they might not last for a very long time. On the other hand, mergers have more short scale order and only long scale reversals, which is an indication that they might be more long lasting. This answers Willie's question of how relevant magnetic fields are for dynamics. This parameter called beta or plasma beta or magnetic beta is a fraction of thermal pressure to the magnetic pressure. So if it is close to 1, you expect that magnetic fields are significant in dynamics. If it's much more than 1, it means the thermal pressure dominates and the magnetic fields don't really play a role in the dynamics. And in both the cases of collisions and mergers, again on the y-axis is the beta, they are still quite high, so about 10 to the 2. In the case of mergers, sure, it's around 10 to the 2 near the surface regions, but it's still low enough that they don't affect the dynamics. One of the major differences between collisions and merger products in our simulations was these radial outflows. If you remember in the plot I showed you before, collision products were just rotationally flattened, but the merger products had these underdensities near the axial regions, which here they turn out to be outflowing gas, outflowing material. Yeah. So here we plot the radial velocity on the x-axis, 0 radial velocity approximately, and by the way, all these error bars here are like 15th to 85th percentile, approximately 1 standard deviation away from this from the mean. And in the merger case, you see that the radial outflows are pretty high velocity. They are up to 100 to 200 kilometers per second, go higher near very large radii here. This is
along the axis.
This is along the axis. These are axialia. It's also, the merger products are also more extended along the midplane as well, so they're more disky in that sense, but they are not, they don't have radial velocity outwards.
So how magnetized are the outflows?
How what?
How magnetized are the outflows?
Okay, I haven't checked specifically for the outflows. I should.
It's basically magnetism of the outflow.
Okay. I haven't checked.
I mean, this is at some particular time.
Yeah, this is after dynamic relaxation, which we assume to happen like 100-ish dynamical timescales after merger.
Persistent outflow, yeah.
There's a what? Persistent? Yeah, it's a persistent outflow, yes. Yeah. I'll just show, actually I can just skip these because there's not a lot of differences here. So we initially select, we choose stars which are around 10 million years in age, so they're still very early in their main sequence. But since they're massive stars, there is some nuclear fusion which has happened. For example, the 10 solar mass star has converted 20% of its hydrogen to helium already. So in the mixing, we also expect some chemical mixing to happen. This is the fraction of hydrogen. Zero-age main sequence stars have around 70% hydrogen throughout, and as they evolve, this part goes lower and lower near the center, whereas the envelope stays around 70%. Due to mixing, there is a dip here, and it's not flat in the envelope regions anymore. It's a more gradual increase upwards. However, both the profiles are quite similar, so we don't expect huge changes in their huge differences in their future stellar evolution. Same with helium profiles, it's just the other way around. Yeah. So that is about these collisions and merger products. I also wanted to talk about another thing I'm working on.
A question that almost anyone will ask you is, what are these going to look like?
What are these going to look like?
Yes.
Yeah, I mean, they're
What
going
are
to
your predictions?
they're going to look like blue stragglers.
Well, no, but using your methodology, you can't yet reliably predict what the evolving star will look like.
Yes.
But you do have some predictions for what the immediate merger remnant will look like.
Sure. Yeah.
And
So
that will be presumably the brightest phase. So, what are you predicting for the transient surveys?
for the transient surveys,
Yeah.
I'm not sure. It's not promising for transient surveys in the sense that it wouldn't be very visible.
With all this outflow, the photosphere is far out. Sure, you're going to see something.
It's going to be as bright as a star can get, I would think.
A different question. I think this is a bit misleading because in a binary merger, you're almost certainly in a state where one of the stars is going off the main sequence. That's sort of the reason why else would it merge. Right? It doesn't have artificial viscosity in its orbit. While a collision, you don't have to have that at all. So I think that in that sense, you're you're comparing very much apples to apples, but maybe you should compare apples to oranges.
That is true, but there can be other ways of merger as well. There can be
I think maybe if you want to do the most common things, you have to do the most common things, right? Of course. And there has been this really nice observational work by the Italian group showing that those trackers are in two channels, and one really looks like mergers and one really doesn't look like mergers. And I think sort of a bit of a missed opportunity to see is that actually true.
No, yeah, that was actually the motivation of the
Okay,
work, to
cool.
see what the observational differences between these two would be. But in the paper you're mentioning, that was by Ferraro, I
Yeah,
guess.
yeah, that's right.
So they're not attributed to mergers, they attributed to mass transferring binaries. So they're still binaries at that point. They haven't merged yet.
No, I don't think so. I thought that there's just has been a lot of mass transfer and there is a white dwarf left. But I mean, that's not that different from a merger.
No, I'm pretty
Maybe
sure
I'm
the
wrong.
two tracks were for binary mass transferring binaries and for collisions.
I thought that there's unstable phase in it. Okay, maybe we
Okay,
should
we'll talk
check
about
it.
stable,
And actually
right.
also more a direct question. You said that the magnetic field is not very important compared to thermal pressure, but isn't the relevant thing to compare with differential rotational energy? Because that's what drives the magnetic fields in the end.
That is a small part of it, but
But
most
then it should be much more comparable, right?
the
If you
differential
compare with
rotation
the energy in differential rotation.
Yeah, but the magnetic field amplification is not completely due to just differential rotation. It's because of small scale dynamo. It's the turbulent energy converting to magnetic energy.
Are you sure?
Yes.
But isn't it originally driven still, but it also could be by the.
It's only a small part. It's definitely a fraction, and that could explain that that's the difference between collisions and mergers, because one of them is more differentially rotating than the other. But the major exponential increase in magnetic field is because of the small scale dynamo.
Okay, just to ask, so Allison wrote a paper with me 25 years ago. It was a similar question of what happens when you merge two stars, and what's the impact on the blue stragglers. For example, if you mix them completely, then you get fresh. The star merger thing going in might have half, in your case, half its helium, half its the core is highly enhanced in helium. But after you merge, if you mix it all up, it gives it a second life, and you live twice as long as a blue straggler as you would have if you started off half burned out. And there were previous claims is that there's almost no mixing, that you can skip the simulation and just reorder all your elements by entropy.
Yeah.
And then you don't need to do any simulation, you get an answer, and then you get a short-lived remnant. And then I don't know what changed, but I don't know if anything changed since then. But then Allison in our paper said that, if you do Eulerian simulations, then you get 20% mixing, which is still very small, that it gives a small enhancement to you, a small extra life, but nothing close to a factor of 2. Is that still the case, or is that,
Yes.
does this change the answer?
This is not complete mixing as well. It's still true, yeah.
Sorry?
This is not full mixed as well. There is some mixing.
In her paper, it was 21% in 25 years ago. What is it now?
Yeah, it's around the same. It's around 20-ish, 30-ish.
20 to 30%. So it's
Yeah.
still a similar. So you get a small extension on life.
Yeah. And the entropy sorting you mentioned is also what we expected initially. We do see that for the merger products, but we don't see it for the collision products. We're still trying to explain how exactly to work that out, but yeah, that's something we have to figure out.
Can you show the chemical composition helium? So how much?
Yes.
So how much on the one hand on the merger section? How much of the outer and the merger part? How much of the outer envelope is actually eventually lost? Therefore, you get a more helium-rich atmosphere.
Okay. Firstly, this part of the star is very low density, and we shouldn't trust this result so much because our resolution, even a high resolution simulation, doesn't physically explain this part.
That's a lot of mass.
What?
I mean, it's not just the atmosphere.
Oh, I meant here in this
I
part.
know, that's a lot of mass. There are a couple of solar masses.
Yeah.
So that's not that low density.
Okay. So you're talking specifically of this
No, I'm just
material.
curious how much material actually get strung away.
Oh no, there's not. It's more than 97% of the mass is still bound to the star.
More than 9,
97.
97.
Yeah. So there's actually there was a study. I forget the author. I think Gleibeck or one of their collaborators, who estimated that depending who have like a quantitative formula where they predict how much mass loss happens based on the mass ratio of the collision, and for these kind of mass ratios, more than 95-96% of the mass is still bound to the remnant.
Okay. So you cannot make a helium-rich star to say.
No, you cannot strip it away. If that's your question.
There was a
Yeah,
paper
it's
today.
for
I think.
collisions. Yes.
Also, so another question, I think your 10 plus 5 is really very different on the left from the other two. Am I just interpreting it right, that in the 10 plus 5 case, the very center of the star is the core of the low mass star, and then you get the core of the high mass star, and then sort of some mixture?
That's true. That's exactly true. That's again because it's more dense.
Right, so the density contrast is much bigger between
And
those.
the bump is because the 10 solar mass star is much more evolved than the 5 solar mass star.
So in that sense, the entropy mixing, you have to be a bit careful, right? It actually does depend on, well, maybe it is assorted by entropy, I guess.
Yeah.
Okay, anyway, thank you.
Yeah, so wait, anyone else has questions on this? Yes.
So does changing the resolution of numerical simulations, does that affect the final plasma beta that you have in these simulations?
The plasma beta. Okay, so we checked for the magnetic field strengths, which is essentially checking for plasma beta, I guess. And we did resolution tests so that the magnetic field saturation happens, that saturation doesn't change much with resolution. Yeah, so the resolution which we have is for the 5 solar mass star around 1 million star cells, and for the 10 solar mass 2 million, so it's in that 1 to 2 million cells per star is our resolution.
Sorry, million or billion?
Million. Wait, billion?
10 to the 6.
Yeah, 10 to the 6, yeah. That's still pretty expensive though. Yeah. So I just want to digress and talk about tidal disruption events. If anyone's not familiar with it, there's an illustration of it. So you have a star and a black hole, and the star goes on a orbit around the encounters a black hole in a single encounter, and if it's within the so-called tidal radius, this is when the tidal force is approximately the same as the self-binding energy. It can get stripped away, or it can get tidally stripped away, and there's a part of the star which falls towards the black hole, part of the star which goes away. So with this, this also can happen for other objects, for example, white dwarfs. So you can have a tidal disruption of a white dwarf. I just showed 2 cases here. Both are the same mass black hole, same mass of white dwarf as well, but one of them is a normal tidal disruption where it's just a stream of material which is flowing away from the black hole, but the other one is a fanning of material. This is a supernova. Here there is runaway fusion which happens near the pericenter, and the energy ejected from it fans out the material, and you can also see this observation. Obviously, both of them are observations.
How is the burning triggered?
How is the burning triggered? Like physically, you mean? Or
Well, I mean, is there a shock going through the star? Is there some sort of, the adiabatic compression just by itself?
It's compression, yes. It's tidal compression.
If the star starts cold, is that going to really be enough to ignite?
Yeah, it's still, it's firstly it's a white dwarf, and yes, it is enough to ignite if there's enough kind of compression.
Why?
Because it reaches the pressure, the density.
Wow.
So you're putting a very, very massive white dwarf already, right?
No, this is not a massive white dwarf. This is like the peak of white dwarf is like 0.6 solar masses.
Yeah, it's compressed by it.
Yeah, so
I mean,
it has to go very close to the black hole. Yes, these are very close to the black hole.
well, that's a factor.
It's almost a factor 100 you have to compress the density, that seems a lot.
Well, yeah, Martin, you're getting stretched into a thin ribbon,
Yeah,
right? So it's getting really pulled out, and so it's really pushed in into that thin ribbon, so you can't get these large compression factors. But I agree, you have to get very close.
Yeah, it is very close. So these are much rarer than even normal white dwarf tidal disruption events. But these are kind of transient, which could be observed for sure.
Well, okay, but then to repeat Martin's question, what is the compression you're getting?
The factor you mean?
What's the peak density you get? I mean, eventually the density goes down because it gets pulled apart.
Okay, I can check this, and I have it in my computer. I can just check it and get it after the talk.
If you only had test particles and no interaction between them at all, that's minimal question. Also, these test particles are mostly uncompressed under tidal disruption.
Yeah,
So this
that's my
is
impression too. I mean, it's a modest effect.
So this is all due to degenerate waves going through. I mean,
No, I think one needs to do some resolution tests here.
Because the white dwarfs kind of disrupt way before it reaches the pericenter, right? If you make the impact parameter very small, so you actually get stretched, and
Yeah.
so I don't see how much it makes. I don't see how it helps to have a very small impact parameter. Yeah, anyways, I think I agree with all this point. I'm surprised.
Okay. Sure. Anyway, yeah, so this is just for the changes in isotope fractions as a function of the impact parameter. Here, impact parameter is defined as, again, the scale impact parameter defined as the periapsis distance divided by the tidal radius. So it's as a ratio of tidal radius as well. Yeah, so you have isotopes on relevant isotopes on the y-axis and impact parameter. So this is a wider impact parameter, and here is the closest impact parameter on the right. And these are isotope fractions after pericenter passage. So all the runaway nuclear fusion happens right at the pericenter passage because of the compression, which I mentioned before. We can talk about this later as well. And specifically, if you look at nickel 56, which is an indicator of how much of a supernova, for example.
So this is still a 0.6 solar mass white dwarf, and you burn everything to nickel?
Yeah.
That just seems very hard to believe.
Yeah. But yeah.
This is Roger Bradford's idea, like 30 years ago.
Well, but
There was-
I think it's good to try to actually calculate it.
Yeah.
I mean,
There was,
I'm just surprised. My surprise may be misplaced.
There was this paper by Stephen Roscoe, which also did this for a wide suite of simulations, and they also observed such supernovae.
Can you tell us more about what's going on inside the code? How the
Yes, so this is a nuclear reaction network, which is from this, it's like package of calculated rates of nuclear reactions. So for each cell, of course, there's a whole reaction table or whatever, which is inputted into the code, and depending on the temperature, pressure, and everything, you change the chemical fractions, and the extra ejected energy is added as internal energy to the cell. So this is a very consistent. This is also done for many hydro supernova simulations using multiple codes like Gadget, Repo, other ones. Even many white dwarf binary simulations, if you're familiar by Rudiger Buck-Moore.
Yeah, my student worked with him on merging white dwarfs and finding similar magnifications in magnetic fields as you find for the main sequence stars. So that part, yay, right, great. That's such a good mechanism. Again, this just surprised me, and it doesn't mean that I'm right at all.
Okay.
Because you have to burn almost the whole white dwarf. That is
Yeah.
hard. Because how can you get all of the density? Well, I guess once there's a shockwave going out, maybe it's okay. Just do it by temperature, but that won't.
Okay. Well, yeah, so that's it. So here I end with my summary. And I just mentioned with our collision and merger project, we are also going to evolve our final resultant products using a 1D stellar evolution code like MESA to see their long-term evolution. This has also been done in the past, so this will be a good comparison to see how they differ in the long term, if at all. We don't expect it to, but we should see, of course. Yeah, that's it.
earlier about the magnetic field amplification, and it might be a question of vocabulary that you kind of said initially that but if you just did trace up, you have to trace the particles, which gives you some map from the initial fluid position to the final merger product. And since you know the relative position, if I just draw lines there, I just draw magnetic field labeling lines, the lines will get longer, and therefore the magnetic field will get stretched and will get larger. And that effect, I guess, I would have called it the passive kinematic stretching, which the question is if that is what accounts for the final field, and that's one possible scenario. And of course, the differential rotation will keep winding it up for a long time, whereas the other thing is over in the dynamical time. But I think some people, when they say dynamo, mean a nonlinear coupling of the field actually affecting the fluid motion. So I think that's a slightly different effect. So with a dynamo, I think most people, that a dynamo is an active feedback where the field reacting on the fluid actually matters. Just so I have a feeling you are saying it's the first, that's the kinematic winding. And I think that's why but you have the answer, so maybe it would be interesting to compare if the magnetic fields between the passive winding and what you actually get, because I think the simulation has a back reaction in it. You can compare. If it's similar, then it's one thing. If it's by many orders of magnitude, then I would have called it a dynamo.
Okay. Yeah, sure. That's a comment, right?
Sorry?
That was a comment, right?
So there was something that I was asking that you can go back and you can tell us the answer.
Yes, it's a comment. Do Bruce structures rotate near breakup?
No, so there has to be a mechanism to spin.
They don't rotate
spin
very
down.
slowly.
Uh,
They rotate very slowly, or
they don't
does it
rotate.
have-
I think there's like a wide range of rotations, but they don't rotate near breakup. To answer your first question,
Right.
so there has to be a spin down mechanism, and again, one of the suggested mechanisms is through magnetic fields, magnetic braking.
So, okay, so you would say that supports the magnetic field is present. Another way that if you simulate the same thing, but with hydro only, it could be faster rotation than the one you would get?
No, it would, I mean, with the simulations it would be similar because it doesn't affect the dynamics.
Okay,
Yeah, but
that's true. So when does it come in? When does the
oh,
magnetic come
it
in?
happens at much longer time scales. Magnetic braking happens at much longer time scales.
You mean the accretion disk is formed or something that
Uh,
carries a momentum?
Yeah, something like that.
There's
So
no magnetized wind, right? We're not talking about magnetized braking, magnetic
there
braking.
could be magnetic, like the disk braking as well, or the wind braking as well. I'm not sure how wind braking would work here. There could be some because these are massive stars, and there would be magnetized wind as well.
I thought they don't have much magnetic wind.
Which
Massive
massive
stars,
stars?
yeah.
Because they don't have a magnetic field, but
They
these
don't
do have a
These do
magnetic
have a
field.
field.
But also
So
they don't have,
they have
right, they
strong
have,
winds, right? So
Yes.
but that's, those that have, they have no, right, they have no dynamo, no surface magnetic, this one has surface.
These ones have, yeah.
But don't you also need a corona?
no, I don't think so. In fact, there is this very magnetic O star in Orion, probably a merger product, rotates super slow and has trapped wind in its magnetosphere. So you just need a wind and a magnetic field, and most O stars don't have magnetic fields.
Yeah, I don't
These
think-
ones
Don't
would.
you have to heat up the material to near escape to use the magnetic field to lose the momentum?
You just need an ionized wind, right?
If they're O stars,
So who drives the wind? Oh, because
Line
radiation.
driven, yeah.
it's line driven, it's
Radiation.
O stars,
Radiation drives the wind. But this is.
B stars, yeah, B stars.
I see. I see. So you can lose it later. Thanks.
I think these would actually be BE stars, so decretion this would be more.
Yeah,
more
The
reasonable.
ROE stars.
The boost striker is not always E star, right? It can be A stars, right?
Yeah, actually, yeah, typical Bruce triangles which you see in the globular clusters are not even A stars. They're
Right, F stars.
yeah.
So how do they lose the magnetic lose momentum?
Magnetic braking. But they
But they don't
lower
have
mass.
corona. They don't have corona. How do you?
F star does.
And no
They're after G
radiation.
stars, they have,
G star does, the F stars don't.
well, if they've got extra magnetic field, it would.
No, you need turbulence to generate corona.
No, I mean, you got magnetic fields in it.
But okay, sorry, that was my
Okay,
short questions that how
Okay.
do they look incremental, right?
sure.
Any more questions? Any questions online?
Yeah, I mean, it must be good. Yes. Thank you so much.
Okay, if that's the case, let's thank Pavan again.
Thank you for correcting my study. So now,
Yeah.
yeah, so I think. Actually, we can do something
direct collision rate is low, like head-on collision is low. Most of them is probably, but I think this might be useful for galactic centers because at some time stage, they cannot do off-center collision. Only thing they can do is head-on collision. Because the velocity is too high. Velocity is like hundreds to thousands kilometers per second.
Okay, so those would not, these are parabolic encounters? Zero
Yeah,
energy
those
orbits.
will, so
Those would
those,
have excess energy, so they would completely disrupt the stars.
oh, so you will not even have a merger collision product.
Yeah, and if you, even if you did, it would be very much smaller than that. I don't know exactly how it is.
But that might give you a wider transient if you combine the whole thing.
Yeah.
Otherwise, I don't know the head-on collision for 10 to 5 solar stars where that happens. Seems like the rate would be low. Like mergers should be everywhere, but head-on collisions probably not that easy. But if it's in galactic centers,
It should be,
do head-on collisions.
Just from star, like single.
Yeah, because
because any grazing collision would just go away.
we will just go past each other. Yeah.
Do you think you can differentiate between like whether the G2 like objects in the galactic center are merger products or collision products?
What are the G2?
The G2 objects are like the sort of extended gaseous clouds. Like there was, I think the first one was identified in like 2012 or so. And there was a bunch of work after that to suggest that they're collision products, but I say collision in the sense of like either collision or merger in your context. But there were some papers in the mid-2010s that were saying that you can form them by doing fungible lead-off Kozai cycles, and then you get to a really high eccentricity for your binary, and then your binary merges at high eccentricity, or collides at high eccentricity. So I think that would be pretty similar to the collisions that you have here.
Yeah.
Just because like you're getting up to a very high eccentricity, and then you have like a
high eccentricity collision. Yeah,
right,
sure.
right.
Yeah, so if that is the mechanism,
But
I'm not familiar with the object, but if that's the mechanism, yes, they should look like collision.
But then my question comes in. So I've got a paper that is in press right now that is not yet on the archive, but we're basically arguing that instead of having these high eccentricity collisions, you should shrink to near contact separations through tidal friction. Like tidal friction is basically way more efficient than they give credit for. And so then you would still get these G2-like objects, but only in post-main sequence evolution. So I guess that's not something that you're directly modeling because you're looking at main sequence stars that are spiraling into each other. But I guess that could still be, like, I guess what I want is to really easily say that G2-like objects come from these slower in spirals or like some common envelope phase rather than direct high eccentricity collisions. And I'd be curious to know if like that's an observationally differentiable thing that we can do right now, or okay, yeah. Anyway, look into G2-like objects. G2 objects. I can send you some of the papers.
Yeah, fair.
I'm sure you've come across it.
Okay.
Anyway, nice talk. Sorry you got interrupted so many times.
I mean, it's the speed of 7 minutes.
Yeah.